is stress due to shear force. And this is always going to be an XY stress element. It makes sense if you think about it like this. So let's say we're looking at a beam from the side. And let's say this is the X location where we're trying to see what's going on. And let's say that we're looking at a set of stress elements like that, okay? Can you see what I'm trying to draw here? Well, the shear force looks like this, right? And so that naturally, that's naturally going to correspond to tractions like this on those little stress elements. And since our coordinate system has the x-axis that way, the y-axis that way, and the z-axis that way, those little stress elements are on the x face if you have a positive shear force, right? If this is V, then these are going to be, I'm not going to write it on there because it'll look clever, but these are going to be XY stress elements. See that? They're on so, take one of these stress elements out of this strip, okay? These downward blue arrows are on the positive X face, and they're aiming in the negative Y direction. And so even though there's a sign we have to deal with, the signs are going to be flipped, but you can just see that shear force is just intuitively contributing to a XY stress. I know you can see that. Don't act like you can't see that.
No, I think never was.
That's what I want. That's great. Okay, beam requirements. For this approach to calculating the stress due to the shear force. Well, there are only two shapes that we can deal with. The first one is a rectangular shape. A rectangular cross section. And we also, for these results to be good, we need the height to be greater than the width. It's actually sort of the bigger the width is compared to the height, the worse the results are, and it's a sliding scale. So our best results are if it's really tall and skinny, and and if it's a square, I don't really know how far off it would be. I could calculate that. Um, but if you have a, let's, for our purposes, let's just say square um, is the widest and shortest that we're gonna take as acceptable. Okay. And the only other possibility, so rectangular, and then the other possibility is a circular cross section. Well, with a rectangular cross section, we can do it at every Y location along the cross section. With a circular cross section, we can only do it at the neutral axis. But only along the neutral axis. Well, that sucks. Um, might as well not know anything about it then, except, well, it turns out that the neutral axis is where the stress due to shear force is the biggest. So if you have a really significant stress due to shear force, at least you can figure out what it is at the maximum. That's where it has the greatest absolute value. Okay, so notice what's happening here. We didn't have any restrictions on the stresses we could calculate due to tension compression. But for the bending moment, we had some pretty strict requirements. And now for shear force, we have some strict requirements. And so if you're looking for beams where we're going to be able to calculate the entire stress tensor, we're going to have to take like the intersection of all of these requirements. It's not like we're taking like you're adding like taking this extra space, the space you get from the bending moment requirements plus the space of solutions of allowable cross sections that you get from the shear force. It's you need things that where they both apply. And so notice that was so badly said, but notice with each new set of beam requirements, the options for acceptable beams are getting reduced. So now if you have a internal loads problem where so you solve the internal loads and you get bending moments at the point you're interested in, and you get shear force at the points you're interested in. Now you can only calculate the stresses if the thing is a rectangle, or if the thing is circular, but then you can only do it at the neutral axis. All the other things that were allowable for calculating stress due to bending moment have now been thrown out. Okay, and it has to be straight, and it has to be prismatic. So I'm just trying to stress how important this stuff is to consider, like when you go out and you look at, like in dynamics today, when like we looked up and we're like, oh, I wonder what the stresses are on that thing. You got to think like, is that panel straight? Is it prismatic? Is it rectangular? Is it, and you have to go through each one of these. And if it doesn't meet those criteria, then the approaches that we're using, you can't do it on that. Yes. Well, really like you would. So if you knew a lot about this stuff, um, like more than I know off the top of my head, you could come up with some simplifications that would give you some okay answers for it. But really, the short answer is you would go to a finite element software package and you would type in the external loads and it would spit out these answers at you. And the hand calculations that you do using this simplified approach or whatever would only be used to sanity check your answer. Like, do I believe that the computer solution, came out without dividing by zero or whatever? You can sometimes get wacky things in the computer simulation. But the final answer to any kind of like real application is you would get the stresses and strains from finite elements. And all we're doing is just sort of trying to understand in a way like how to interpret that stuff and how to sanity check it. That's all we're learning this stuff for, really, and except for the handful of people who will go into writing finite element software. Um, so before we can, the formula for the stress due to shear force is tau xy. So that's the shear stress in the xy spot is equal to negative. So again, the sign will work itself out for you. V times Q over I sub B. And so we're going to have to define what this Q means. And we'll be able to use that formula. No, it's not. It's different. It's just one of those times where you have more mathematical things than you have letters in the alphabet. So, uh, and remember with bending moment, I'll say one more thing. I'll say this again next time, but with the bending moment, by thinking about how the shape, like you bend a bar like this, and then you can intuitively figure out that the top of that bar that you bent is going to be in compression and the bottom is going to be in tension. You can figure out intuitively why this negative sign is here from this picture, because this is what, with our sign convention, this is what we call a positive shear force. I don't know whose idea that was, but that's what we do. And a positive shear force corresponds to downward XY stresses, but downward XY stresses on the X face, that's in the negative Y direction. And that's why those are opposite of each other, the sign. Okay, any questions? All right, so we'll finish shear force next time. Yeah, exactly. Except it's not even, I think that somebody was, that one's even funnier in a way, I think, because, okay, so back to the stress due to shear force. So what I said was the stress, it's going to be a shear stress, and it's going to be the XY element. And the value is equal to negative V, that's the shear force, times Q divided by IB. B is the width of the cross section at the point in question. And so to use this formula, the only thing we need to know is this Q. Okay, so I have to tell you how to calculate that. And I don't, this is the first moment of, I suppose it's the first moment of area. I don't know of people calling it the first moment of area. So I'm just going to call it Q. Okay, so let's say that we start with an arbitrary cross section. Okay, so let's say that's our cross section, and this is we're imagining like the beam extends back into the page. We can't trust if we had a cross section like this, we don't have any techniques that would accurately calculate the stress, but this mathematical thing Q still has a meaning for this. And let's say this is the neutral axis. That means that it goes through the centroid of the shape. And let's say we want to calculate Q at this line. So we want Q here. Okay. Then take the area that's above that line and locate its centroid. So this is the centroid of the whole cross section. This is the centroid of the area above that line. This shaded region has an area A. And then calculate the distance from the neutral axis to the centroid of the shaded area. I'm going to call that distance D. Then Q is equal to the area times that distance D. One really interesting mathematical fact, it makes you want to go through try to prove it. Cool factoid. Q using the area above the line, the line of interest, always equals Q using the area below the line of interest. It's not the same area or the same distance, and they always equal each other for any shape. So, in other words, so if this is your cross section, and here's the neutral axis, and this is your line of interest, this is the neutral axis, then you can calculate this two different ways. You get the same thing. So there's the neutral axis. Here's the line of interest in both cases. You can calculate this area A, this centroid, and this distance D. Or you can calculate this area, this centroid, and this distance D. Isn't that cool? Somebody prove that. You have to use integrals and stuff, though, to do it. Prove it for a rectangle, though. You can all do that. All right, so now we know how to calculate everything we need to figure out the stress. So let's do problem. So let's say we have a cantilever beam. And let's say it has a length of 2 meters. And we're interested in what's happening right at the midpoint. And let's say that the cross section of this beam is rectangular. If this is the neutral axis, let's say that, so the whole thing has a height of 0.1 meters. And we're interested in this line halfway between the neutral axis and the top. So this is 0.025 meters, and this is the line of interest. And the thing that's causing this stress is just going to be the weight. We'll say the mass is 100 kilograms. Yes, we do need that. 0.02. Okay, let's think about what we have in this problem for a second. We know how to do stresses due to three kinds of loads: tension, compression, bending moment, and shear force. Of those, what kind are we going to have here? We're going to have bending moment and shear force. The bending moment, okay, so what if our line of interest was the neutral axis? Which of those two loads that we have, bending moment or shear force, would contribute to the stress at the neutral axis? Shear force, but not bending moment. And actually, the shear force is biggest at the neutral axis. I should have said that. I'll say that in your notes. So it's always the shear force is going to be biggest at the neutral axis. What if the line of interest was the top or the bottom? What would contribute to the stress at those lines? Bending moment would be at its two extreme values, but the shear force would be 0 because you'd have no area above that line or below that line. Okay. So in order to have both of those two things, we have to be somewhere in between the neutral axis and the extreme edge. Okay, so we don't have to calculate the external loads to do this internal load problem. I'm going to do a cut. Just, we know the line that we're interested in, so I'm going to do it right at x equals 1 meter. Then we don't have to get anything in terms of x or anything. So this length is 1. That's half of the length of this. So it's going to be half the weight. The full weight is 981 newtons. So half of the weight is 490.5, and it's going to happen right at the midpoint. And then we have the tension, shear force, and bending moment. So Newton's second law says 0, negative 490.5, plus T negative V is equal to 0. And so T is 0. We saw that that was going to be the case. And V is negative 490.5. And then the moment equation. So first we have a force of 490.5. What's its moment arm? 0.5. And is it a clockwise or counterclockwise moment? Clockwise, so this is all negative. And then plus M minus V times, what's its moment arm? It's X, but X is equal to 1 in this case. So this is equal to 0. So we have M is equal to 245.25 plus V. So that's minus 490.5. And so the bending moment is negative 245.25. This is newtons, this is Newton meters. If you take the derivative of negative 245.25, you don't get negative 490.5. Is that a problem? No. Why? So what's going on here why isn't that a problem? It's not a function, exactly. You can't, So in order for dm dx to be equal to v, you have to know what these are as functions of x. This is just a single snapshot of a single instance, so you can't take derivatives. Basically, we'd just be checking like if this was a constant m function, but we don't know that that's the case, and it's not. All right, so the total stress tensor is going to be the stress tensor due to tension plus the stress tensor due to bending moment plus the one due to shear force plus the one due to torque. Those two are 0, and so we only have to worry about bending moment and shear force. Okay, so for bending moment, we know sigma xx is equal to negative my over I. We have to calculate that I. It's a rectangle. The rule for rectangles is I is equal to 1/12 times the base times the height to the third, and that is 2 times 10 to the minus, oh man, minus times 10 to the minus 6. Okay, and that's meters to the fourth. The y that we're interested in is y equals 0 is at the neutral axis, so y is positive 0.025. And so the stress is negative of negative 245.25 times 0.025, yep, divided by 1.6 repeating times 10 to the minus 6. And what do you get for that? Okay, times 10 to the 6 pascals. And so the stress tensor due to the bending moment is 3.68 times 10 to the 6. Zeros everywhere else. This is pascals. And now the stress due to the shear force. It's going to be the Xy shear stress, and it's equal to negative VQ over IB. We already have I. So for this cross section, this is our area. This is our centroid. The distance we want is this. So area is equal to 0.02 times 0.025. So that is 5 times 10 to the minus 4. And that distance, remember, you're going to the centroid of that area, not just to the line that you are interested in. So the distance is you can think of it as 0.025 plus halfway to the top, 0.0125. So 0.0375 meters. And so Q is 5 times 10 to the minus 4 times 0.0375. And what do you get for that? To what? Okay. And the units, that's meters cubed. And then B is just the base at the line of interest. This is a rectangle, so that is just 0.02 meters everywhere. Tau xy is equal to negative shear force, so negative of negative 490.5 times Q, 1.875 times 10 to the minus 5th, divided by I, 1.6 repeating times 10 to the minus 6 times B. Cancel out all the tens before you do the division. It'll save you a bunch of round off error. You can think of that as 490.5 times 18.75 divided by 1.6 repeating times 0.02. And what do you get for that? 2.76 times 10 to the 5th pascals. And so the stress tensor due to the shear force is 0, 2.76 times 10 to the 5th, 0, 2.76 times 10 to the 5th, zeros everywhere else. And so the total stress tensor is, just add those two together. Well, you added element by element. So this is just going to be 3.68 times 10 to the 6 for x, and then 2.76 times 10 to the 5th. And if this beam was made out of a fairly brittle material, and you knew that because it's brittle, it's most likely going to fail in shear stress, you would want to calculate the maximum shear stress produced by this loading at whatever point you're interested in. So how would you calculate that? Yep. Now calculate principal stress tensor and then the maximum shear stress is equal to sigma 3 minus sigma 1 over 2. And you compare whatever value you get here with whatever the value is for the brittle material that you're considering to see whether you're worried about it breaking or not. Yes? To find like where it would fail for that material? No, it's not. It's not dependent on the stiffness matrix. It's dependent on other stuff. So you could have two materials with the same stiffness matrix, but one can you can deform permanently forever. You know, like a steel bar, you could, I don't know how much, but you can bend it down to bend this bar, not with your hands like I'm I'm bragging, but it can be bent to a very noticeable angle and still be perfectly strong, you know. Um, if you found some kind of ceramic material that happened to have the same stiffness as steel, before you even saw it bend, it would break, you know. And so that's just a property of like the, you know, the microstructure of the material. That's something you'd have to look up that people would have done lab tests to figure out. And by the way, so when I say a brittle material, well, you would never really make a beam out of a brittle material, I'm guessing, but maybe you would for some reason. Um, but so if you had this ceramic thing, that what brittle means is that you can't deform it permanently very much before it breaks. Once it leaves that linear elastic range, you're basically done being able to deform it before it snaps in two. Whereas metals, and some metals more than others, this wouldn't be a very useful criterion for figuring out when it's going to break, because, you know, metal, you could bend this beam over at 90 degrees and it would still hold. So then you have to use sort of more complicated calculations to see whether you're worried about it breaking. Although this would still be useful for determining whether you're concerned that this steel bar is going to deform permanently if you're trying to avoid that. Max? Yep. You just plug that into your eigenvalue calculation. It gives you your three principal stresses. For triangle rule. Oh, for this? Um, yeah, right. I don't know what it is, but there is. But you know, how much easier could it be than plugging that into your calculator and calling the eigenvalue function? Any other questions? Okay, that's all. Good luck tomorrow, everybody. That sucks, man.